From our discussion of simple acoustic wave, we have seen that the simple acoustic wave propagates with a constant wave velocity and the shape of the wave is permanent, that is, it propagates without any distortion. However, these properties that we have found for a simple acoustic wave comes because of the linearization of the equations that we have used, and that linearization, as we have seen, is coming from the assumption of infinitesimal amplitudes and gradients. That is, we have assumed that the disturbance are infinitesimally small and their gradients are also very small, which has helped us to linearize the equation, and because of that linearization incorporated in the equations, we found that the waves move with a constant speed, the acoustic speed, and the wave shapes remain undistorted. However, in many practical situations, these assumptions are not possible. That is, we cannot assume that the disturbances are very small and their gradients are also small, and when these assumptions are not possible, the condition at any given point in the wave cannot be approximated by those in the undisturbed fluid. Under such a situation, the wave velocity varies from point to point and the simple wave becomes distorted as it propagates. To describe this type of waves with finite amplitude and finite gradients, we need to solve the complete nonlinear equations. However, complete solution of the complete nonlinear equations are extremely difficult, and in many cases that is not possible. So, we will try to get it in an indirect manner instead of solving the nonlinear equations directly. Let us consider a plane compression wave moving to the right. Let us say at two adjacent points, that is, let us say at two adjacent points, the fluid properties differ in magnitude by d p for pressure, d rho for density, d u for the particle velocity or flow velocity. That is, let us say the flow velocity here is u, here it is u plus d u, the pressure here is p, pressure at this point is p plus d p, and so on for all other quantities. Now, the respective parts of the points, the respective parts of the wave that is passing through these points also differ in the wave speed, let us say by an amount of d c. Wave through these points differ in wave speed by d c. That is, if the wave speed here is c, here it is c plus d c. Now, as long as the velocity and temperature gradients are moderate, the viscous at heat conduction effects are negligible, and this finite wave this finite wave can be thought of as a succession of infinitesimal pulses. Now, each part of this wave travel at local speed of sound with respect to the fluid in which it is propagating. Consequently, the propagation velocity of a part of the wave with respect to fixed coordinates is then propagation speed with respect to fixed coordinate with respect to fixed coordinate is c equal to u plus a. Now, the propagation velocity of the adjacent parts of the wave is c plus d c is u plus d u plus a plus d a, or d c is d u plus d a. Differentiating this with respect to p, we have d c d p Now, for a rightward wave, we have already seen that du dp equal to 1 by rho a, and hence we have d c d p to d a d p plus 1 by rho a. Now, considering that the entire fluid was originally at rest with uniform pressure and temperature, then each particle of fluid undergoes isentropic changes, and consequently, the increments in pressure and density between adjacent fluid particles obey increments in p and rho between adjacent particles satisfy which gives 2 a d a d p and hence if we change this derivative with respect to rho, it becomes d d rho of d p d rho by d p d rho. Now, substituting this relation here, we get at constant entropy. Now, using specific volume, V equal to 1 by rho, so that d d rho becomes minus and we get so this relation gives how the local wave speed changes with the pressure P. Now, for a fluid d p d v at constant entropy is negative. So, sign of these d c d p of course depends on sign of the second derivative of d c d v d p d v. So, d p d v is negative. So, sign of d c d p depends on that is the sign of d c d p will depend on whether the isentrope is concave upward or isentrope on the PV diagram is concave upward or concave downward, that is on whether isentrope on the PP diagram is concave upward or downward. And we can also see that when dCdP is positive, it implies that the higher pressure part of the wave will have higher speed than the lower pressure part of the wave. That is, higher pressure parts of the wave will overtake the lower pressure parts when dCdP is positive, and that will happen when d2p dV2 is positive, and the opposite happens if dCdP is negative. That is, when dCdP is negative, the lower pressure parts will overtake the higher pressure parts. Consequently, this means that a compression wave will stiffen as it progresses when d2p dV2 is positive. However, the compression wave will flatten if d2p dV2 is negative. So, the results you can write that compression part of the wave or compression wave stiffen and expansion wave flatten when is positive. That is, the isentropy is concave upward. This is of course, the usual case for all real fluids. The other alternative, that is when d2p dV2 is less than 0, then compression wave will flatten and expansion wave will stiffen. However, no such real fluid exists, and consequently, in all cases the compression wave stiffen and expansion wave flatten when a wave of finite amplitude propagates through that fluid. If the isentropy is straight line, that is the second derivative d2p dV2 is 0, then of course, the wave speed remain constant. If isentropy is straight line, and wave is undistorted. Let us consider the perfect gas. For perfect gas, we have and in a perfect gas we can clearly see that the wave will distorted in such a way that the compression part of the wave will stiffen and the expansion part of the wave will flatten. Now, looking to the problem from the point of an observer who is moving with the local particle velocity, the acoustic theory applies locally. Consequently, relative to an observer moving with the local fluid velocity, the wave at the point propagates with local acoustic speed. So, relative to an observer, moving with local fluid velocity or particle velocity, the wave at that point propagates with however, relative to the fixed frame of reference, but relative to fixed frame of reference, as we have already mentioned, to fixed frame, relative to fixed frame reference, propagation speed is for a rightward wave. So, for both left and right moving waves, both left and right moving waves C equal to plus minus A plus u, or the plus is for the rightward moving waves and the minus is for the leftward moving waves. As you have seen, the wave speed is no longer constant, as well as both A and u are also not constant, and u may not be negligibly small, and the gradient of u also may not be small. So, evaluate these in terms of the density, we can apply the acoustic theory locally. And considering perfect gas, considering perfect gas, we have P by rho to the power gamma equal to P 1 by rho 1 to the power gamma, where P 1 and rho 1 are the pressure and density of the undisturbed fluid, and by rho, and where A 1 is the speed of acoustic wave in the undisturbed fluid, that is when the conditions are P 1 and rho 1. Applying acoustic theory locally, we have du equal to plus minus A d rho by rho and substituting A here, we have now this is integrable, and we can see that u equal to minus 1 by 2 minus 1, which of course can be written as plus minus 2 by gamma minus 1, and taking A 1 inside and substituting A 1 equal to we have A minus A 1. This gives A equal to A 1 plus minus gamma minus 1 by 2. So, this relates the local acoustic speed with the acoustic speed in the undisturbed fluid and the particle velocity, and substituting this in the relation C equal to plus minus A plus u, we get C equal to or also in terms of A1 is the speed of sound in the undisturbed fluid and rho 1 is the density of the undisturbed fluid. Of course, the fluid in this case is a perfect gas, and this gives the local wave speed of a wave with finite amplitude or wave with disturbances which are not small. Now, once knowing this, the variation of wave speed in terms of density, let us now consider the propagation of a simple wave of finite amplitude. Consider propagation of simple wave with finite amplitude, that is the wave which is being produced by disturbances which are not infinitesimally small. Now, let us consider a wave, and let us say which is the density disturbance that is that condensation parameter delta rho by rho 1, which we have earlier defined as bar at time t equal to 0. This is t equal to 0. We consider for a rightward propagating wave, the wave speed is c equal to u1 to 1 plus gamma plus 1 by gamma minus 1 . Now, let us see what will happen to this wave as time passes. What you see that at the region where rho is greater than rho 1, c is higher than a 1, and where rho is less than rho 1, C is smaller than A 1. Thus, the wave speed changes in the region of higher density, the wave speed is higher, in the region of lower density the wave speed is lower, and consequently the wave as it propagates owing to different speed at different point on the wave shape will not remain as it was and it will distort it. And we see that region where the condensation is higher, that tends to overtake the region where the condensation is lower. In the region of higher condensation, the characteristic lines are inclined more, since the slope as you have seen earlier is proportional to the wave speed. Consequently, let us say that at this point where the density is constant, the speed will remain same as A 1 and the characteristics line will be like this. However, at this point which has the highest density, the characteristics will incline much more and will no longer remain parallel, but will have much higher slope. At this point of the wave, again the density ratio is 1 and consequently the wave speed will remain same as A 1 as it here, and the characteristics line here will be parallel to the characteristic line here. Similarly, here also the characteristic line is parallel to the characteristic line here and here. At this point where we have the lowest condensation, this will have a slope which is inclined much less and will move like this. Now, let us consider a time t 1 So, we will take this shape. Now, what you see that we have already mentioned that the wave as it propagates is distorts the region of higher condensation, it tends to overtake the regions of lower condensation, and the regions in terms of compression and expansion region, the net effect is that the compression region is steepened and the expansion region is flattened. In the compression region, the characteristic lines converge, while in the expansion region the characteristics line diverge. In the compression region, as you have seen that if we consider even a case like this, this will be the shape of the wave at so as the wave propagates according to this theory, this will be the shape of the wave leading to this situation at time t equal to 3. Of course, this is physically not possible, because it implies that there are 3 values of density at a particular given point in this region. This of course cannot happen, and consequently we can say that this situation will never reach. In fact, even the situation that is shown at T 2 will also not reach. The simple reason is that as considerably well before this situation occurs, the velocity and temperature gradients reaches to such a high value that the viscous effect and the heat transfer effects are not negligible, and the diffusive actions are considerable, and their effect will be such that to counteract this steepening tendency. So, before this situation reach, the diffusive actions are becoming considerable, and they will counteract with this steepening tendency that comes because of the nonlinearity in the wave or the nonlinearity in the equations, and these two opposing effects will reach a balance, and the compression part of the wave will become stationary, in the sense that it will not change any further. However, this situation will eventually reach well before the time t 2, and in that case the compression part of the wave has become a shock wave. Now, in the compression part, the isentropic relations are valid until the diffusive actions are considerable, or until the viscous friction and heat transfers are important. When the stationary balance between diffusive actions and the nonlinear steepening effect is reached, the condition across this wave front are given by the shock wave relations, which we have derived earlier, and the intermediate part where the diffusive actions are considerable. However, they are not exactly in balance with the nonlinear stiffening effect. The states are non-isentropic, and they can neither be considered within the isentropic relations or with the shock relations, and the complete unsteady equations, including the viscous and heat transfer terms, are required to analyze that part. That will be somewhere between T 1 and before T 2. Looking to this case, however, we see that the expansion wave always remain isentropic, and as it flattens, as it propagates, and the gradients are continuously decreasing, it never achieves any stationary condition, and the isentropic relations always hold over the expansion part, and since no stationary condition is achieved, there are no expansion shocks in reality. So, what we see that if we have a finite amplitude wave, then the wave, different part of the wave will propagate at different speeds, and consequently the wave will distort. And what we see that the compression part of the wave steepens, while the expansion part of the wave flattens. Due to this steepening effect, the velocity and temperature gradients increases considerably, and subsequently after certain time a balance is reached between the steepening effect due to nonlinearity and the diffusive action due to viscosity and heat transfer, and the compression part of the wave will reach a stationary state and it becomes the shock wave. However, the expansion part, it flattens as it propagates, consequently the gradients become smaller and smaller, and the stationarity is never reached and no expansion shock occur. That is, the expansion part always remain isentropic. Next, we will consider this centered expansion wave. Let us consider that a wave of fluid, certain amount of fluid is allowed to expand suddenly. This can be thought of, let us say that certain amount of fluid is enclosed in a piston within a duct enclosed by a piston, and the piston is withdrawn impulsively. In that case, the distribution of the particle velocity in the first instant is a step, and an expansion wave develops, and since the expansion wave flattens as soon as the wave starts propagating. So, at some time after t 1, the particle velocity will have a linear distribution, and similarly the pressure will also have a corresponding distribution. Let us say that we have a duct in which there is a piston and this is The velocity distribution you can let us say that this is the original at t equal to 0. An expansion wave develops instantaneously. However, as the expansion wave begins to flatten as soon as the wave starts propagating. So, after certain time t 1, and similarly the pressure distribution will be at time t 1. Now, the front of this isentropic wave, if we consider this in an x tree diagram, the front of the isentropic wave propagates at the speed of sound of the undisturbed fluid. Hence, the front of the wave propagates with speed, let us say a 4 into the undisturbed fluid, that is in the opposite direction of the piston or in the fluid motion. The wave speed in the portion of the wave which is behind the front is given by, according to that theory that we discussed earlier, as c equal to a 4 plus gamma plus 1 by 2 u. Now, see that the wave speed decreases continuously, since this u p is, or absolute of u p is positive of course, and minus u p. So, the wave speed continuously decreases. As we can see from here, the wave speed continuously decreases. These fans of straight lines that we are showing here are lines of constant c and thus of constant u and rho. These are lines of constant wave speed lines of constant wave speed, and of constant u and rho. Hence, these are basically characteristics lines. As time increases, this fan becomes wider and the wave becomes flatter and flatter, and the gradients of velocity, density, pressure, temperature, they become smaller and smaller. Thus, the waves always remain isentropic. The terminating characteristics is given by a 4 minus gamma plus 1 by 2 u p into T, and this will slope to the right or left. Terminating characteristics T, and this slopes to right or left depending on whether A 4 is greater than gamma plus 1 by 2 u p or A 4 less than gamma plus 1 by 2 u p. Between the terminating characteristics or behind the terminating characteristics, the fluid properties have the uniform values. Behind terminating characteristics, fluid properties are uniform. We will continue this in our next lecture, because few more things are to be